Okay, in the name of Allah, we start our next class. Do you have any question from the previous content? Actually, what we have covered last time was why we should go to binary system, the numbering system of binary, and then we talked a little about converting decimal to binary and binary to decimal. Is there any questions? Okay, we can continue. Now we go to another base. Another base would be octal or hexadecimal. In octal, we mean base 8. So we talked about base 10, which is decimal numbering system. Then we talked about binary, which the base is 2. And now we are going to talk about octal, which the base is 8. As I've told you before, when the base is something, then it means that we have that number of digits in that system, in that numbering system. When we are saying that we are in base 8, it means that we have 8 digits, 8 signs. 0, 1, 2, 3, 4, 5, 6, 7. So we have these digits in this numbering system. As you could see, 8 is a power of 2. 2 to the 3 is 8. So if we have numbers in octal, they have some kind of relation to the binary. We will see it soon. And for hexadecimal, the base is 16. When the base is 16, it means that we should have 16 digits, 16 signs in that system. And the digits would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have these digits in decimal. And then we use letters A, B, C, D, E, F. A is a digit in hexadecimal numbering system. B, C, D, E, F. So when you are saying, for example, we say we say, for example, 2. It's not writing. Oh, okay. No, it's written. It should raise. For example, we say a number. Let's say 3b. 3b. In which system? Hexadecimal, in base 16. Again, the same things that we told about decimal, we told about binary, it applies here. What we said? We said the value of a number is if you have some kind of this point, which is hexa point here, and you have something in the fraction part, and you have something in the integer part. The integer part, the value would be weighted by the power of 16. So the first one will be multiplied by 16 to the 0. The next one would be 16 by the 1, and so on. 16 to the 2, 16 to the 3, and so on. So this number, the value of this number in decimal would be how much? B. B is like 11 in decimal. 11 times 1, 16 to the 0 is 1. So 11 times 1 is 11 plus 3. 3 times 16 to the 1. 16 to the 1 is 16. 3 times 16 is 48. So this is 48. 48 plus 11 would be 59. So 3b would be 3b in hex or 16 would be 59 in base 10. 59 in base 10. 3 times 16 plus b times 1. b is 11. So, okay. The other thing that we could mention here is if you want to convert it to binary. Let's do this by 59. 59 is decimal, and we have talked about how to convert it to binary last time. 59. 59, I use subtraction, successive subtraction. 59 has 48. 69 has 48. 48, no, 48 is not the power of 2. 59 has 32. It has 16. 13 plus 16 is 48. So it has 8. 48 plus 8 is 56. And then it has 2 and 1. 2 and 1. So this is 59. So if we convert it to binary, would be 1. 1 is there, so we have 1. We have 2, so there is 2. We don't have 4, so it is 0. We have 8, which is 1. We have 16. We have 32. That's it. So 59 would be 11011. Now, if you look at this number and then you compare it to our hex value 3b. I've told you hex 16 is 2 to the 4. So every 4 digit of binary represent 1 digit in hexadecimal. Did you understand? Every digit in hexadecimal corresponds to 4 digits in binary. So it's very good. It's very simple. Converting hex to binary and binary to hex would be very easy. How? Okay, let's start from here. We had 3b. 3b. I've told you every digit in hex converts to 4-digit binary number. B is what? Is 11 in decimal. All, if you look at here, I've written for you. B is 1011, 11. 8 plus 2 plus 1, 11. So B would be 1011. And 3, so each digit could be converted separately. It's very easy. It's not like decimal that you have to do successive division or successive subtraction. No, every digit separately. 3 in binary would be 1, 1. So if you want to put 4 digits, it would be 0, 0, 1, 1. And B would be 1, 0, 1, 1. Okay? So the number 3B is equivalent to 1, 1, 1, 0, 1, 1. Look at this. 1, 1, 1, 0, 1, 1. So we could change binary to hexadecimal, hexadecimal to binary very easily. The reverse part. For example, you want to convert this one, 1, 1, 1, 0, 1, 1, to hexadecimal. What you do, you separate 4 by 4 and then convert them to hexadecimal. 1, 2, 3, 4 would be here. Let me put another color. How could I put another color? Okay, for example, we use this one for the separator. 1, 2, 3, 4. So one digit would be this. And 1, 2, 3, 4, which would be 0 for the next digit. So this digit, 1, 0, 1, 1. 1, 0, 1, 1. 8 plus 2 plus 1 is 11, which is B. 0, 0, 1, 1 would be 3. So it is 3b. 3b. Okay? Converting hexadecimal to binary or binary to hexadecimal is easy. The same almost for octal. For octal, there are 3 digits. Every 3 digit of binary numbers correspond to 1 digit of octal. So let's see some examples. To do conversion from 16 to 2 or 8 to 2, from 8 to 2, each 33 bits of binary correspond to 1 digit. For hexadecimal, every 4 bits correspond to 1 digit. Okay. So for example, this one. We have already seen 35.37 in decimal would correspond to this. You could convert it right now. We had talked about this last session. So now, if you want to convert it to octal, to base 8, you separate 3 from here, 3 from here, 3 from here, the integer part separately, the fractal part separately from here. So again, 0, 1, 1. 0, 1, 1 in octal would be 3. 0, 1, 1 is 3. Okay. Then we have 1, 0, 0. 1, 0, 0 would be 4. We have 0, 0. So it is 0. At the fraction part, we have 0, 1, 0. 0, 1, 0 is 2. 1, 1, 1 is how much? 1, 1, 1? 7. 7 and 0, 0. So it would be 3, 3, 3. So it would be, as you see, 4, 4, 3, 2, 7 in octal. Easy, good. It is good because it is just each digit could be converted separately, or each 4-bit converts to 1 digit. Or we can do that the same for hexadecimal. If we would like to do hexadecimal, we have to separate 4 by 4. So again here we have this 4, we have this, and that side like that. Okay. Now we convert each 4 bits separately to its corresponding digit. 0, 0, 1, 1. How much? 3. 0, 0, 1, 0. 2. 0, 1, 0, 1. 4 plus 1. 5. 1, 1, 0, 0. 8 plus 4. 12 would be in corresponding hexadecimal digit. B is 11. C. Oh, it's here. Oh, you could see it here. C. 11, 11, 1, 1, 0, 0. It's C. 12. B is 11, A is 10, and D, E, F. So it is like that. You see? 23.5 C in hex. You could convert it very easily. Okay. Okay, during the class, I would like to try something. If you liked it and if you participate, then we could continue that. Otherwise, we could leave it. I put some questions here, and I need this speed. I want you to do it fast. And the first two people who submit the correct answer would get point for, could be collected for their final grade. That's it. But it would be better if I could put some questions for making group work. But for this session, we do it individually, and then we go for that. But how are you going to submit your answer? Let's try to see if it works. Let me see if we could do it here. I am not sure, because as I told you, I am somehow new to Brightspace. I'm trying to learn. But what it came to my mind was using a discussion forum. And a discussion forum in here, numbering system, okay. Where is that? I had some competition here. What happened? Let me find it in discussions. Discussions. Competition. Oh, okay. Where is that? Do you see that in your writer space? Competition. No? Why is that? You could? Okay, good. So this is the competition. And somebody posted something because you didn't know what's that, so it's nothing, it's okay. Sounds fun, okay. Nasser, where is Nasser? Nasser? Yes, he's not, he is not here? No. But, okay. Yeah, we could try. So what I do, I start a new thread. I call it question number 1. Question number 1. Where is number? Number 1, which would the problem I will tell you in the class with the PowerPoint. Please post your answer. You should reply to this thread, and that would be your answer. So question number 1. Question 1, okay? So you could be ready for that, so just reply to that. So what is the question? Question number 1. The 2 people who is doing the first, so we can see the time of your submission. So the octal representation of 185 in decimal, and you have to change it. I hope you don't use calculator, but if you use, it's your choice. But I guess you could do it faster by brain. Post in the. Why is it May 5? Could you reply? Is it working? No problem? Working or not? It says May 5. Why it says May 5? This one. You should post to this one. Question number 1, not that one. I hope you didn't do that. This one. Question number 1. So I delete this one. I hope you haven't replied there. What? Did you?
You have to create a thread before you can reply.
What should I do?
I'm saying that you have to create a thread before you can read any other threads.
Okay, yeah, you create your own thread, you reply to the thread, but you can't see the others' answers. But you can reply, no?
We have to create a thread before we can read it.
So you cannot see if you click on that, then you can't have reply to thread? No?
We have to make a thread before we can ever even reply.
So it's not good. So I should change it. No, it's not here. Okay, too bad. So we have to try it again. So ignore this question. We will change it. But let's go to the discussion. These things I have to learn. And then we go to competition, edit. So I change this one. User must start a thread. So save and close. No deadline. Okay, no restrictions. But we just consider the first 2. Okay, so everything is okay, is open. Save and close. Okay, discard that question, we change it and you try again. Okay, this is the competition, and this is the new. I should delete this one if I could. Oh, okay, I could delete this one. Okay, what? Let me delete this one so we don't have this. Okay, and then tell me what should I? No, this is not good. Okay, you tried to post something which was my mistake, and so I delete this question answer, but this is the one that I've created, and you have 2 replies here now. Okay, but it's not good because we lost the time. I change it and I ask you to reply again. So if I go there, we had 2 replies by Zhizheng and Dan. So we had 2 replies, but we don't consider this. I apologize from Zhizheng and Dan, but we try again. So this one is not considered. Again, view topic, competition, start a new decade. I am saying new question 1. New question 1. So post your answer to this one. There was one error. Post is required. What's that? I don't understand these things. New question 1. I have to have what?
Yeah, otherwise it won't work.
I have to, what to do?
Like in you see how you have 0 words in the thread?
Here, I have to do something. Okay. Reply to thread. No. I will change it. I will change it because we have already lost. Okay. So this is the new one. The new reply to this thread. I hope it works this time. So let's change it. So this was the question. I should change it. We change it to 205. Start, please. Okay, reply. I guess you do it fast now. Some of you know how to do that. Two is enough. New question 1. Where is that? Oh, in this one. 8 replies, but we consider the first 2. So let me see if it is old by old, newest first, oldest first. Okay, first one would be Shishang. Shishang, are you here? Okay. So 341. 340. I don't know if it is correct or not. We will see. Laurier. Where is Laurier? Okay. 315 and Dan 315. So if 315 is correct, then Laurier and Dan would get the point. If not, Shisheng would be correct. So 341. What was the question? It was 205 in base 8. 205. So it is 5 times. I have to make it again, the pen. Okay. 5 times 8 to the 0, 8 to the 1, and 8 to the 2. 8 to the 2. 8 to the 2 is 64. So 2 times 64 is 164. And 5 times 1 is 1. So the answer would be 160. What's the local button? Oh, this is decimal. What I am doing? This is decimal. So decimal. Decimal, we have to find the number in 8. What should we do? Divide. Divide by 8. 205 divided by 8. I usually use subtraction, which is easier, but let's try. Let's see if I could solve this problem. I could ask from Laurier to come here and to solve it, but we can try it. Yes? Okay, 25 times divided by 8. What is the answer?
So you get
25. Okay. 25 times 8 is 200. So you have the division as 5. Okay. Then 25 divided by 8, it is 3. So the divide would be 1. And 3 times divided by 8 would be 0, and the remainder would be 3. So the answer would be 5, 20, 513. Yeah? Or the 3, from that side, 315. So what did you write? Okay, 315. So we had two, Laurier and John. Okay, the next one wouldn't be considered. So next time, hope you could do it faster. Okay, thank you. We should do it in group. It would be good if we could do it in group. But let's do it individually today, but later we do it in group. So now we have talked about binary, and we saw that binary represent numbers. Okay, so that's good. When you have a number in binary, then it represents either a number in decimal or octal, or they are all the same. They are numbers, the same numbers, but it's represented in different bases. But we can represent something else with these numbers. This process, when we represent something with numbers, is called coding. Coding is that when you code something, you change it from one format to another format. It is some kind of coding. For example, you do video coding, and when you do video coding, you get a video and convert it to, for example, MPEG-4 format. MPEG-4 is a format of binary numbers, 1 and zeros. You get a video and then convert it to MPEG-4, or an audio converted to MP3. MP3 is a format of files of numbers of 0 and 1s, but it represents an audio file, an audio a voice, an audio. So this is coding. Now we are going to see some coding here, some examples of coding. The first one would be signed numbers. Up to now, whatever I've told you up to now, they were unsigned. We were writing 200, for example, 255 in decimal, and then you convert it to binary, which would be 11111111. You convert it to hex, which would be FF, and so on. So this is unsigned numbers, positive numbers, all considered positive. So what do we do with signed numbers? If we have negative, -2, -10, how do we do that? For signed numbers, we are going to define the leftmost digit, the MSB, the most significant bit, the leftmost digit, as the sign. In a signed coded system, we consider the leftmost digit as the sign. So we have sign and magnitude, sign and the value of the number. So if the sign is 0, it means positive. If it is 1, it is negative. Sign and magnitude. So 1 bit here, and as much as bits you want here. For example, this one, consider this as the magnitude. How much would it be? Let's see, 1 plus 2, 4, 8, 1 plus 8, 9, 16, 32, 64. 64 plus 9 is 73. So this number, the magnitude is 73. So if you put 0 at left side, then this number would be positive number of 73. If you put 1 here, then it is minus 73. Plus 73, minus 73. So the magnitude is there. The leftmost bit would represent the sign of the number. The sign would be either positive or either negative. 0 corresponds to positive, 1 corresponds to negative. So this is the sign numbers. The next coding, we called it BCD, binary coded decimal, BCD. We talked about converting decimal to binary. You do, for example, successive division and you find a binary number. You could do that. But sometimes, like what we told in hexadecimal, that you would like to have each digit correspond to whatever it is. So for each digit, you do it the conversion separately, so it would be easy. But when they are together and you have to do it successive subtraction, that's harder, that's difficult. Sometimes only digits would be important for us in a decimal. For example, a digital clock which is showing the clock for you. Maybe you have a table clock, a digital table clock in your room. It says, for example, now it is, what's the time now? It is 12:06. 12:06. 1, 2, colon, 0, 6. This is displayed in your clock. So every digit could be displayed separately, and we don't need to go through the difficulties of calculating 1,206. Just 1206. We want 1206. So we convert it, we code it separately. So a system of writing numerals. A 4-digit binary code to each digit, and the digits in decimal would be from 0 to 9. 0, 1, 2, 3 to 9. So this is the number, the coding. The coding would be that. So in this coding, if we have, for example, the number of 59, and I tell you to convert it to BCD, so it means that 5 should be converted, 9 should be converted. 9 is 1 plus 8, this is 1, this is 9, and 5 is 4 plus 1. 4 plus 1. So this is 59. This is 59 in BCD. You see, it is somehow similar to hexadecimal, but they are not the same. You know that they are not the same. Why? For example, if I add 1 here, 59 plus, let's say 2. 2 in BCD would be this. So if I add these things, you should add it in BCD. In BCD, it means that this is 9, this is 2, so 9 plus 2 is 11, so you have 1 here, and you have 1 as a carry, and 1, it is 5 plus 1 is 6. So the result would be this, 0, 1, 1, 0, 0, 0, 0, 1. You know, if you wanted to add in hexadecimal, the result wouldn't be this. What would be the result at that with hexadecimal? The result would be 5B and 9AB. 5B. But here, with the result would be 61. 61 in BCD. Okay? Very simple. Just the digits convert to 4 bits. Every digit, 0 to 1. Yeah, this is another example. 387, which means 3, 8, 7. 3 separately, 8, 7. So it is BCD. So the next coding system that I introduce would be 7-segment. 7-segment is just some kind of coding that I don't know if you have worked with 7-segment. Did you? With 7-segment? 7-segment is this one, this device. This is a 7-segment. Have you worked with that before? Maybe. Yeah, in your courses or in your home. I don't know, in your projects, on the projects. So this is 7-segment. So what does it do? It has how many LED segments? 1, 2, 3, 4, 5, 6, 7. It has 7 segments. And with these 7 segments, you could show the numbers and even the letters in English, A, B, C, D, E, F. For example, if we want to show letter D would be something like that. Where from those 7 segments, this would be D, yeah? And again, this would represent 0 also, yeah? So we have only 7 segments you should play. But let me just use it for the numbers. This is 0, this is 1, only 2 of the segments are on. 1, 2. 2 is, this one is on, this one is 1, this is 2. 3 is, this is 3, and so on. 4, for example. 4 is like this. 4, 5, 6, 7, 8, 9. Okay. So each number, when you want to display it on 7 segments, it would be like that. Okay. So what are we saying here about coding? Each segment, A, B, C, D, E, F, G, as you see here, if you consider it as a bit, would be either on or off. So it would be either 0 or 1. So, for example, the number 1, which is easier, it has 2 segments. The number 1, which segments are on? B and C. Is that right? B and C. These 2 segments are on, the others are off. So if I want to represent it with 7 segment representation, A would be 0, B would be 1, C would be 1, and the rest would be 0. 1, 2, 3, 4, 5, 6, 7. This is the BCD representation of 1. You could write it for 9, you could write it for 8, 7, whatever you want. So this is another kind of coding, another kind of representation that I wanted to show you here. So let's see all of them. Yes, please.
So each letter corresponds to a certain number?
Each letter or each digit?
Well, when you show like the 0, 1, 1, 0, 0, 0, you're showing 1, because you have a diagram and it's saying 8.
Yes. No, we don't go to ABC. You could do that also, but we just use 0 to 9, okay? Let's see 0 to 9, or even 0 to 9. Or even we could go to A, B, C, D, E, F for the hexadecimal also. But for if you want to show G, well, how do you represent G with 7 segments? I don't know. Could you? G. For a small g, we could. A small g would be something like that. Maybe this is a small g, but for big G, I don't know. You might be able. I am not going to think about this right now. But for the numbers, you see, this is 0, and 0 is, which one are on 0? 0 is this one, this, this. So A, B, C, D, E, F are on, and G is off. As you could see, A, B, C, D, E, F are on, and G is off. So this is the number. This is the representation of 0. 1, 1, 1, 1, 1, 1, 0. Or for example, let's say 7. 7. 7 is, let's see, 7. 7. 7 is this one and these 2. This is 7. 7. So A and B and C are on, and the rest are off. So again here you see 7. 1, 1, 1, and the rest are 0. So this is another kind of representation. And you could use it in your projects. We will use it. You have 7 segments on your board, the board that you are going to use in the lab, and there are connections to the 7 segment. We have 2 kind of 7 segments common anode or common cathode. If they are common anode, it means that the anode is common and the cathode of each LED segment is for you, A, B, C, D, E, F, G. So if you want to turn it on, you should put 0 at the cathode, and 1 is common. Anode is common, so you put 1 here at this point. Where is the anode? Here. Here is the anode. Is connected to 5 volts. You put 1 here, and then each one of segments that you would like to turn it on, you put 0 at the corresponding segment. So this is common anode. If you use a 7 segment of common cathode, that it's not shown here, but in common cathode, you put the cathode to the ground, and then each segment would be 1. You put a 1 there, so it will be turned on, each segment that you want. But I wanted to show you here something. We have a special design which might I might ask you in the lab to design something like that. We have a chip called BCD to 7 segment decoder. This chip is doing the same thing that we have discussed. What does it mean? It means that if you have a 4-bit input here, for example, I put 1. 1 would be 1. 1 would be 1, 0, 0, 0. 1, 0, 0, 0. If I put 1 here, 0 here, 0, 0 here, then it will generate, what does it generate? I forgot. 1. It will generate this pattern, 0, 1, 1, 0, 0, 0, 0, and it goes here, so it will generate this pattern at the output, and it goes to the 7th segment, and it will be turned on. A 1 will be shown at the 7th segment. So this is a specific chip for BCD to 7 segment decoder. In our course, we are going to design something like that. We have to build a truth table for what would be the input, what would be the output, and how you make the circuit, the design, so with this input generates that output. With the other input, it generates another output, and so on. So this is what we are going to do in our course. The next coding system would be gray code. Gray code means, let's look at the numbers in binary. 0, 0, 0, 0 is 0. Then we have 0, 0, 0, 1 is 1. Then we have 2. Then we have 3. Then 2 is this, 2. Then we have 3. Then we have 4. So on. You continue. If you look at here, for example here, you look at these two numbers, these two successive numbers, 3 and 4. There are 3 bits have been changed. 1 changed to 0, 1 changed to 0, 0 changed to 1, and 0 remains 0. So we have the successive number that they change, the number of bits changed there is more than 1. We only had 1 change in the number, but the bits have changed. 3 bits in 4-bit number, 3 bits have been changed. For example, here we have 1 change. Here we have 2, this one and this one. Here we have 1, but here we have 3, and so on. Okay. When we have this kind of coding, then if you have a design which they will produce successive numbers, which it usually happens. When you are doing some kind of design, it usually happens that you have successive numbers one by one. For example, you are writing some data into the hard disk. So when you are doing some data in the hard disk, you do it one by one. You put it in the first location, and then the second location, and the third location, and so on. 1, 2, 3, 4. When you do this, then in the electric circuit, if we have lots of changes of the bits, they will interfere each other. 0 to 1, 1 to 0, 0 to 1. And if it is a lot, then it will interfere more. So it is good. It is a good practice for design that we build something, some kind of code that will make one by one. So it goes one by one. It changes only one bit with successive numbers. We call this gray code. So a gray code means a code that represents the numbers, but in a way that each two successive numbers change only in one bit. So let's see how did they do that. You could think yourself of that and build something like that, but I will show you the result. For switches, when you have 0 to 1 or 1 to 0, it's not good. So it's better if we have less transitions from 0 to 1. And so we will go to gray code. Gray code. For example, this one. This is a gray code. No, this is the binary code. This is the binary code that you have too many. For example, this is 4. I don't know what is this. Okay, this is 7 and then goes to 4. No, this is not the 4. Let me show you. This is the gray code. So you see here, this is the binary. This is the gray code. Number 0 represented by 0 in binary, but in gray we put 0, 0, 0. Number 1, again the same. But number 2, in binary it is 0, 0, 1, 0. In gray it would be 0, 0, 1, 1. Number 3, 0, 0, 1, 1 in binary, 0, 0, 1, 0 in gray, and so on. So you could see they designed some kind of codes where two successive numbers would only differ in one bit, 1, 0 to 1 or 1, 1 to 0. Only one change. And this is their solution for 4-bit. You could find it for 5-bit or 6-bit or 3 bits or whatever you want. So my next question for you to come to take part would be, I am asking you right now, start number 3. Question number 2. Question number 2. So reply to the thread. So the question is this. To give you a hint, look at this table. If you could, you want to write it down or say, take a picture or somehow. So this table would help you for solving the problem. Okay? This is the table for gray code for 4 bits. So 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Now I am asking you to write 3 bits gray codes from 0 to 7 and write it in the thread. Just post it there. From 0 to 7. I could bring the table for you also. Why did I tell you to take picture? I could leave it here. Okay. So two first people. Person. Question number 2. Okay, we have Samuel, we have Rainak. I hope they are correct. Let's see if they have written correctly. 0, 0, 0. This one change 1 bit, 1 bit, 1 bit. Yes, 1, 1, 1, 1, 0. Oh, this is not correct. Oh, this is not correct. So let's go to the Rhineck. 0, 0, 1, 1, 1, 0. Oh, this is not correct. This is not correct. We have 2 changes. So the next one, volume. So you have 4 bits. Why did you write 4 bits? You had to write 3 bits, volume. Jeff. 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, okay, 1 change, 1, 1, 1, 1, 0, 1, 1, 0, 0. It seems correct if you haven't put some kind of repeating there. It seems not. I guess this is correct. Jeff. And Shota. 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1. But yeah, correct. So I guess Jeff and Shota made the correct answer. Jeff? Where is Jeff? Jeff, okay. And Shota? Perfect. Very good. So, very good. Actually, the table could help you because if you look at the table, I am going to use this table to write for you 5-bit gray code. If you have it's some kind of recursive solution. This problem has some kind of recursive solution. If you have the answer for 4-bit, you could write the answer for 5-bit. How? These are the first 15 digits in 5-bit also. Then we start from, again, the same one. So these are, let me say, these are the first 17, but put a 0 here, 0, 0, 0, 0, 0, 0, 0, 5-bit, make it 5-bit. And then the next one would be 1 with this number, 1, 0, 0, 0. 1, 1, 0, 0. Oh, it's too bad because my pen is not very good. So I hope you saw what I wrote. 1, 1, 0, 0. So, and the next one would be this one. This one with a 1, and then this one, and then this one. You go in the reverse order, and you complete your 32 bits. So if you look at here, you see the same thing from 3 to 4. So these are the 3 parts. 3. You put 0 at the left side for all of the 8 bits, and then you go the reverse part. 1, 0, 0 is this one. What's happening? Okay. Yeah. 1, 0, 0, and then 1, 0, 1, 1, 1, 1, 1, 1, 0, and then put a 1 at the left side. Okay. So this is the gray code, which is somehow interesting. So the next one, ASCII code. ASCII code is American Standard or Coding International, something like that. I don't remember the abbreviation. ASCII code. So what's that? Up to now, we were just talking about some kind of numbers. In 7 segments, we have some kind of displays, but usually they are numbers. But what if we want to represent letters? You want to represent, for example, hello, hi, the word hi, which has 2 letters, H and I. How to represent it in binary? Because we are going to have everything in binary we are talking about. So they created a system, ASCII, as a standard. So digits 0 to 9, lowercase and uppercase letters, 26 lowercase letters and 26 uppercase letters. They have codes here. 26 plus 26 is 52. 10 digits is 62, and then we have some normal characters that we usually use. Then it came out as a set of 128 letters, and they put a binary representation for each letter. For example, I remember hexadecimal value of hexadecimal 30, which is 48 decimal, represents the letter 0. So 0 here is 30 hexadecimal, not 0 at the binary system. 0 as the ASCII is 30. For example, letter A corresponds to 40 hex, which is 64 in decimal. 40 hex corresponds to letter A, a capital A. This small a would be, I guess, 60. I have the table next page. So 96. 96 is the value for a small a. Oh, okay, it's here. Okay, this is the number. This is the letters and the corresponding numbers. Did I say right? A. A is 4. Oh, 41. I made it right. Got right. 41. 41 is A, not 40. 40 is at sign. Okay, and A, small a, is 61. 97. But remember, these are hexa values. You see, it goes up to F. For example, letter less than would be 3C. 3C. 3C represents letter less than, and so on. For example, tilde, so on. Okay. Okay. Oh, sorry. No, don't see that. Okay. The question number 3. This is our last question for today. Question number 3. Which I don't know the answer myself. I should find it. Question number 3. Reply. So the first two, who wrote the? No, not this one. No, this is not correct. No, it's coming in the page. It's on page. So don't consider that. So this is 128 symbols, and which were this? Here we cannot find, for example, a letter E with accent. I guess in French we use that, or other languages. We don't have it here. So what do we do for those letters? They started to extend it, and they use 8 bits. So because 128 is 7 bits, you could represent all of them with 7 bits. And then all those letters, they were representing 7 bits, and we put a 0 at the left side, so it became 8 bits with 0 here and the rest there. So that was the standard ASCII codes. Then they have extended it. Leftmost bit of 1, they put a 1 there, and they've extended it. Some kind of special characters, characters from other accents and so on have been added. Okay. Now I want you to find, with this extended ASCII character set, the ASCII code for copyright symbol. I don't know what's the answer myself. I will try it later. 0 to 5. Let's see what you write, and then I try. answer question number 3. Okay, 184. Wesley. Jeff, D0. D0 is 184. Are they the same? 13 times 16. How much? We will calculate. Don, 169. So who is right? Who's doing right? Shota, 169. So let's see which one is correct, which I don't know. Let me Google it. I am sure that you have done maybe the same thing. ASCII code for copyright symbol. It says 169. Could we trust him? Yeah, could we trust? It's 169. Oh, okay. I could try it one way. Let me see if I could try it. 169. Okay. I try to see if it works. I press Alt and then 0169 on the numeric pad. Oh, it's correct. It's correct. To find out if you have the ASCII code of something, but you don't have it on your keyboard, you want to type it, press Alt and then 0 and the number 169. It's copyright symbol. So it's correct. So who wrote 169? 169. Jeff, D0 is how much? Is 169?
I just used the chart.
Okay. But if you don't, you had another chart?
No, the chart it says CR, and that's at D0.
Oh, D0. D0 is CR, carriage. It's a carriage return. No, it's not copyright symbol, yeah. So 169 done, and I guess these two were the one that they got the previous answer, yeah? Shota, where are you? Okay, you're Shota, yeah? Yeah. Okay. The previous one, you made it right. Is that right? The previous question. And also done. Done? Done? Okay. Very good. Thank you. So let's continue. Now, let's go to binary arithmetic. What time is it? 12:38. Okay. So I guess I stop here. We go to the quiz because we need the quiz to be done, and then we come back if we have time. Let's go to quiz. Quizzes. Online quiz. Binary decimal. This is the quiz. I will make it available for you. Make visible. Please start. Binary decimal conversion quiz. It should be in the numbering system module. Numbering system module. Yeah, binary decimal conversion. It needs a password. Yeah? Okay. Are you ready? The password is DEC, D-E-C, the beginning of decimal. D-E-C, with not capital letters, just DEC.